All right, let's just jump right in. You know, inside every single modern device you own, your phone, your laptop, even your car, there are microchips. But what's inside those chips? Well, that's where things get almost unbelievable. We're talking about a level of tiny, intricate complexity that honestly sounds like it's straight out of science fiction.
And this really shows you the scale we're talking about. The absolute cutting-edge microchips today can have tens of billions of little switches inside them called transistors. And the smallest parts on those transistors, they're only about 45 silicon atoms wide. 45 atoms. So you have to ask the big question, right? How on earth do you reliably build something that complex? How do you mass-produce components so small they are literally invisible to the naked eye and do it for millions and millions of devices all over the world? Well, the answer is a machine called an EUV photolithography tool. Now I know, that is a mouthful. So let's just think of it this way. It's basically a photocopier, but for the nanoscale. Its job is to take the incredibly detailed blueprint of a microchip and stamp it onto a silicon wafer over and over with a precision that is just mind-boggling.
To really get a handle on just how detailed this photocopying is, let's try a little thought experiment. Let's forget about transistors for a minute and just imagine that this machine is printing the words in a book, but on a ridiculously tiny scale.
So in this imaginary nanobook of ours, a single letter would be just 13 nanometers wide. At that tiny size, a whole page of text would be about as big as one of your red blood cells. And an entire chapter, you could fit that onto a single grain of pollen. That's the kind of information density we're talking about.
Okay, let's take this one step further. If you took the surface area of just one typical computer chip, say from a graphics card, how much of this nanotext do you think you could cram onto it? Just take a guess.
You could print pretty much all of it. The entire Harry Potter series. Every single book Stephen King has ever written. The full text of the English Wikipedia. And every book from your local public library. All of it. And here's the kicker. The machine copies that unbelievable amount of detail onto a chip in less than a second.
Now, it's important to remember this amazing photocopier is just one very important step in a huge manufacturing process that happens inside a factory called a fab. To make sense of its role, let's use a simple analogy. Think of building a chip like using a stencil and some spray paint.
See, it's all a loop. First, you coat a silicon wafer with this light-sensitive stuff, a photoresist. Then our EUV machine comes in and acts like the stencil, printing the pattern for just one layer. After that, other tools, the spray paint, come in to etch and build that physical layer. And you just repeat this whole process again and again, up to 80 times, to build the entire three-dimensional chip. That whole journey can take about 4 months to complete.
Okay, so it's time to pop the hood on this thing. How does it actually work? Well, the whole secret, the core of it all, comes down to creating and then controlling a very, very special kind of light.
So, why this specific light? It's actually pretty simple. If you want to draw incredibly fine lines, you can't use a big, thick marker, right? You need an ultra-fine-tipped pen. It's the exact same principle with light. To print features that are just a few nanometers wide, you need a light with a very, very short wavelength. And that's extreme ultraviolet light, or EUV. But here's the catch. EUV light doesn't really exist naturally here on Earth, so you have to make it. And the way they do it is, well, it's incredibly violent. The machine takes these tiny, tiny droplets of molten tin and just completely vaporizes them with a pair of super powerful lasers. It's this insane, high-speed ballet of physics. A tiny nozzle shoots out a single droplet of molten tin. The first laser zaps it, flattening it into a perfect pancake shape. Then, a split second later, the main laser, which is 10 times stronger than what you'd use to cut steel, hits that pancake and blasts it into a glowing plasma. And it's that plasma that finally emits the EUV light we need.
And the speed of this is just staggering. This whole process, shooting a tin droplet and vaporizing it with 2 perfectly timed lasers, happens 50,000 times every single second.
So, we've made the light. Now what? The next massive challenge is controlling it. You see, EUV light is so high energy that it gets absorbed by almost everything, including air and even glass lenses. So the entire path for the light has to be in a perfect vacuum. And instead of lenses, the machine has to use a series of the most perfect mirrors ever made by humans.
And these are not like the mirror in your bathroom. They're called Bragg reflectors. Each one is built from dozens of alternating layers of silicon and molybdenum, and each layer is only a few atoms thick. They're designed so that when the EUV light hits them, the layers work together to reflect about 70% of it. And the surface of these mirrors? They are so flawlessly smooth that across the whole surface, the imperfections are smaller than the width of a single atom. It's just perfect.
You can imagine that this level of engineering requires a totally obsessive mindset. The company that builds these machines, ASML, has a guiding philosophy: meten is weten. It's Dutch for to measure is to know. And it makes perfect sense. You can't possibly control what you can't measure, especially when you're working at the scale of atoms.
And this brings us to the final, absolutely crucial challenge. As you're building that chip, layer by layer, each new pattern has to be placed perfectly, and I mean perfectly, on top of the one before it. We're talking about an alignment accuracy of less than 1 nanometer across the entire silicon wafer. If you're off by even a tiny bit, every single chip on that expensive wafer is completely ruined.
So how do you do this without wasting a single precious second? The machine uses this really clever dual-stage system called twin scan, and it's just a brilliant piece of efficiency. While one silicon wafer is in position getting printed with the EUV light, a second wafer is simultaneously being loaded in and measured with insane precision, getting it perfectly ready for its turn. No time is wasted.
So, okay, after this crazy dive into vaporized tin, perfect mirrors, and atomic-level precision, what's the big picture here? What's the main thing we should take away from all of this?
I think it's this: the technology that powers our entire modern world, our ability to connect and create and compute, it's all built on a foundation of machines that are so complex they feel like magic. They are quietly performing feats of engineering that seem totally impossible, not just once, but millions and millions of times a day, hidden away in factories you'll never see.
And that kind of leaves us with one last thought. The next time you pick up your phone or you open your laptop, just for a second, think about the invisible universe of complexity whirring away inside. And maybe ask yourself, what other impossible machines are out there, hiding in plain sight, making our whole world possible?